Let's take a look at graphing parent exponential functions. Before we do, let me tell you what I mean by parent exponential functions. This is just a general term I use when I'm talking about your starting function when looking at transformation. So a parent exponential function has no transformations. It's just a standard, basically one operation applied, and that's it. Okay. Also, exponential functions contain the variable in the exponent. Okay, so that's what makes them exponential. So we're basically going to be looking at functions like f of x equals some number to the x power. Those will be parent exponential functions. All right, so let's go ahead and try our first one here. Let's graph f of x equals 2 to the x power. And I'm going to do this time by setting up an xy table. And I'm going to go ahead and tell you the x values you're plugging in here will be exponents, so you can choose any number you want. The domain of this function is all real numbers because you can raise a number to any power that you like. So for example, I could choose, what most people choose to start with is 1, 2, 3, you could even do 4. And so let's just calculate the y values in each of those cases. According to this equation, y is 2 to the x power, right? F of x is the same thing as y. So over here, y would be 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, because these are your x values. So this would be 2, this would be 4, this would be 8, this will be 16. And if you were to look at a graph of that, when x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. When x is, oops, sorry about that. When x is 4, y is 16. I'm not going to put the tick marks here now. It's just up here basically. And so you could label these ordered pairs as 1, 2, 2, 4, 3, 8, 4, 16. The y values are 2 to the x value. Okay? And most people stop here. You can imagine what's happening as you move to the right. The graph is getting steeper and steeper and steeper. You get this sort of exponential growth because this is an exponential function. And most people stop right there. Now, you don't want to stop right there because, well, what happens if you keep going to the left? Does anything happen? You should at least investigate it. So for example, you should look at the next x value to the left, which would be 0, and then certainly proceed to -1, -2, -3, etc. And in fact, you can raise 2 to these powers as well. 2 to the 0 power is 1. 2 to the -1 power is 1/2, the reciprocal of 2 to the first power. 2 to the -2 is 1/4, the reciprocal of 2 to the +2. And 2 to the -3 is 1/8. Now if you plot those points, whenever x is 0, y is 1. So you get this point, 0, 1. Whenever x is -1, y is 1/2. Whenever x is -2, y is even smaller. Whenever x is -3, you get 1/8, which is even smaller, closer to the x-axis. But you should be able to imagine that as you move to the left, you're going to keep getting really tiny numbers, positive numbers. So you're going to get closer and closer and closer to the x-axis. And so the graph, as you move to the left of this very commonly known part of the graph, as you move to the left, it's going to decrease like this, sort of flatten out, and keep getting closer to the x-axis. So the x-axis in this particular case is an asymptote. Your graph approaches it. And that line, that x-axis, that asymptote, is represented by the equation y equals 0. because it's a horizontal line where y is 0. Okay? Let's label some more of these ordered pairs. So this ordered pair here, remember, was 0, 1. Maybe let's label this one right here, -2, 1/4, and so on. We could label many of them. We have them in the table over here as well. But there's the graph of y equals 2 to the x. Increases very rapidly to the right, and to the left it starts to shrink very slowly, cutting in half, getting close to 0, but never quite reaching 0. Let's look at another example. Now that we've done this once, we can move a lot more quickly when we graph y equals 3 to the x. And the y values in this case will be 3 to these x values. So y in this case will be 3 to the -3rd, 3 to the -2, 3 to the -1, 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. Well, let's start from the bottom. 3 to the 3rd power, 3 times 3 times 3 is 27. 3 to the 2nd power is 9, 3 to the 1st power is 3, 3 to the 0 power is 1, 3 to the -1 is 1/3, the reciprocal of 3 to the +1. 3 to the -2 is the reciprocal of 3 to the +2, so it's 1/9, and similarly we get 1/27 here. So if we graph these points, let's start at 0, 1, kind of the middle here. At 0, we get the ordered pair 1, or the y value of 1. And then if we put in 1, we get 3. If we put in 2, we get 9. If we put in 3, we get 27, which is 3 times as high as 9. It won't even fit on this graph. So as we're moving to the right, again, our graph is increasing very rapidly, even more rapidly than y equals 2 to the x. And as we move to the left, so I did my 0 and my positive values first. Now I'm going to do my negative x values. So if x is -1, y is 1/3, really far down here. If x is -2, I'm at 1/9 already, very close to the x-axis. And whenever x is -3, I'm even closer to the x-axis, but I still don't quite touch it. So we have the same sort of behavior here. And it's even hard to draw, especially with this tablet. Getting closer and closer and closer to the x-axis. So once again, the x-axis serves as an asymptote. Okay, so we see similarities between this graph, y equals 3 to the x, and the previous graph, y equals 2 to the x. Our asymptote is the same, increases very rapidly to the right. To the left, it decreases, keeps getting closer and closer to 0. Let's look at one more type of exponential parent function. This time the base of our parent function, our exponential parent function, is 1/2. It's a number smaller than 1. And so this graph is going to behave slightly differently than the ones we saw before. Let's calculate the y values of each of these by raising 1/2 to each of these x values. And so 1/2 to the -3rd power, well, let's look at 1/2 to the +3rd power first. 1/2 times 1/2 times 1/2 is 1/8. So 1/2 to the -3rd power will be the reciprocal of that, which is 8. 1/2 to the 2nd power is 1/2 times 1/2, which is 1/4. Which means 1/2 to the -2nd power will be the reciprocal, 4. 1/2 to the 1st is 1/2. 1/2 to the -1st will be its reciprocal, 2. And 1/2 to the 0 is 1, because anything to the 0 is 1. Let's take a look at this graph. So now, whenever, again, let's start at 0. Whenever x is 0, y is 1. Notice that all three of our functions went through the point 0, 1. 0, 1 for this function, 0, 1 for this function. Again, that's because if you raise a number to the 0 power, where x is 0, y is going to be 1. And then If I look at when x is 1, now my y value is only a half. And when x is 2, right, my y value is 1/4. And when x is 3, my y value is 1/8. So my graph this time is getting close to the x-axis on the right side. And so once again, we have this asymptote on the x-axis because we keep getting infinitely close to this thing. So we have the same asymptote still, y equals 0. And then as we move to the left, whenever x is -1, y is 2. Let me move my order pair label out of the way here. Whenever x is -1, y is 2. Whenever x is -2, y is 4. And whenever x is -3, y is 8. So this graph, if you kept going, if x was -4, you get 16. And so the graph here increases exponentially as you move to the left. So it's exactly flipped over the y-axis. And that's because the base here is less than 1. So now you're going to get big y values when you apply the reciprocal, which is negative exponents. So when you have negative x values, negative exponents, this fraction is going to flip over and become a really big number. Whereas before, the bases that we looked at, like 3 for example, base is bigger than 1. And similarly with our first example, 2 to the x, the base is bigger than 1. So that is just a quick look at how to graph these basic parent exponential functions that do not exhibit any transformations.